In this video, we'll focus on how to make mole ratios from a balanced chemical equation. So far we've learned what molar mass is. It's a way to convert from moles to grams or grams to moles. But in the end, again, the goal is for us to be able to, within a chemical reaction, predict how much of something will be made from something else. I like to think of chemical equations kind of like recipes, okay, in the fact that we have both ingredients as well as amounts, and it also tells us what we'd end up making. So, for example, if we had a chocolate cookie recipe right here, we have the what, we have the proportions, and we have the how much they'll make. Okay? Looking at the recipe, you can answer questions like, how much butter do we need per amount of chocolate chip used? So we can say, for every 1 cup of butter, I need 2 cups of chocolate chips. Essentially, I need a 1-to-2 relationship. So even if I had maybe like half a cup of butter, I would still have to keep this relationship the same. So I would know, oh, okay, if I only had half a cup of butter, then I only need 1 cup of chocolate chips. So that's relating reactants together. We can also relate reactants to products. So if I want to make 9 dozen cookies instead of the 3 dozen for this recipe, I would know I need 3 times as much production, which means normally I put in 2 eggs, and this time I would need 3 times that many, so I would need 6. So essentially we're using our recipe and we're relating things together as it is defined within this recipe. So you could create an equality for this, right? We could say that essentially 1 cup of brown sugar equals 2 cups of chocolate chips. In reality, that relationship makes no sense except within the confines of this particular recipe. But with that information, we could always convert from one to another using that as a conversion factor. When I think about chemical recipes, it's the same essential concept. We have our ingredients, so our elements and our compounds, and then in terms of our proportions, how much we have of each, those are our coefficients. So we're used to looking at coefficients and saying like, oh, I've got like, for example, up here, like 2 sodiums and 1 chlorine making 2 sodium chlorides. Okay. In chemistry, the way we count though is mole. So we change the recipe to saying I have 2 moles of sodium and 1 mole of chlorine making 2 moles of sodium chloride. So essentially, the mole is our like cup, tablespoon, teaspoon. They tell us the amount that we're putting in. Okay. So then we can look at a recipe and say, just like we did for the chocolate cookies, well, if I want to make 4 out instead of 2, so 4 moles instead of 2 moles, what would I need to do? And essentially there we're like, oh, we're doubling everything. So I would need 4 moles of sodium and 2 moles of chlorine. You know, if I want to make 10 moles out, okay, well now I'm timesing by 5. So I'd have to put 10 moles of sodium and 5 moles of chlorine. 0.8, okay, well now I'm going less than 2. That's fine, like we can downsize a recipe, but I'd still need to keep that relationship. So 0.8 would mean I need 0.8 sodium and then only 0.4 chlorine. So essentially I'm using these relationships to predict how much of each thing I would need. What I'm doing essentially in my head is making mole ratios. And sometimes it's really easy to do mole ratios in your head and sometimes it's not. So like for this particular problem here, this equation, it's not as easy to do mole ratios because the numbers are like 5 and 3 and those don't divide out quite as easily. So a mole ratio would look like this. The equation is giving us information as an equality. Essentially, in this reaction, 5 moles of O2 equals 3 moles of CO2 every time. And that proportion has to exist. Whether it's 10 to 6 or 2.5 to 1.5, that proportion has to exist. So this is what a mole ratio is. It's a ratio of the moles of different things as prescribed by their equation. So the numbers for the mole ratio are just the coefficients. Okay? That's the information that we use. So if I want to answer that first question up there, how much carbon dioxide would I make from 4 moles? I'd set this up just like a normal conversion problem. Where am I starting? Moles of propane. Where am I ending? Moles of carbon dioxide. And then this will come down the roller coaster to the bottom so it cancels. Where I want to end goes on top. And then their relationship as prescribed by the equation is just a 3 to 1. So mathematically, I'm taking 4 times 3 divided by 1, but chemically, I'm going from a combustible item to carbon dioxide, which doesn't combust at all. So this is essentially stoichiometry. This will be your bridge to the next set of problems, which is going from gram to gram, which is the most practical use of the mole ratio concept. That's it. Have a nice night.